I'm really curious about the next presentation. Xavier will talk about Raman spectroscopy and the everything you always wanted to know subtitle made me curious. So I'm afraid we only have 10 minutes for this presentation, making it even more interesting how to put everything in there in the 10 minutes. At least what I want to know. I'm not how you feel, but I have the suspicion that 10 minutes would also not be enough for anyone in this room to know everything they want. So I'm gonna cut it here. Javi, it's yours.
Well, my name is Xabier Rodriguez. I'm currently a PhD student at the Material Science Institute of Barcelona, where I'm working with Mariano Campoy as supervisor. Well, the title of my talk is kind of a parody of Woody Allen's film. As you know, the title was something like everything you always want to know about sex, but we're afraid to ask. In this case, I will talk about Raman, which is not so interesting, but as sex, I mean. But but well, okay. So this was the poster of the Woody Allen film. So this is what I wanted to imitate here in the cover. Well, the point is that the setup of this film. The Raman scattering occurs, or the Raman effect occurs, when the light is scattered inelastically upon its interaction with matter. And basically, we say that it's an elastic scatter because it loses part of its energy, and this energy is basically lost in terms of, or as a way of molecular vibrations in the molecules or materials we are proving. These vibrations are basically phonons that are activated optically, and the frequency of these phonons depends on the strength of the bonds that are vibrating, and also on the mass of the atoms vibrating. So at the end, what we can collect from a Raman experiment is basically a spectrum of vibrations, which we can typically identify several vibrational windows in terms of the wave numbers with respect to the laser wavelength we are using. Typically, the most interested region in conjugated materials and organic materials is this part here, around 1,017 wave numbers, because it includes all the typical vibrations of carbon-carbon single bonds, double bonds, carbons with nitrogen, nitrogen with sulfur and nitrogen, which are the typical modes that we found in these materials, right? Apart from that, also the Raman scattering is an in situ characterization technique and also non-invasive if the laser intensity is tuned accordingly. It offers diffraction-limited lateral resolution to do maps, for example, as I will explain later. We can tune the laser so as to enter into resonance or out of resonance in our material and improve the Raman cross-section. It's material selective because each of the materials will provide us a unique vibrational fingerprint, so it will be a very important tool to chemically identify materials when they are blended, for example. And there are also a couple of, well, these are already one of the most interesting uses of this of Raman spectroscopy is that, for example, we carry out this work in methylamine lethalide perovskites, collaboration with the Imperial College, in which we basically studied the phase transitions with Raman spectroscopy in these materials. And also, apart from phase transitions, we can also study, for example, the degree of molecular order in polymer fluorine blends, also with Raman spectroscopy. Because I don't have too much time, I cannot enter into the details of these two papers, but I will focus, for example, in the fingerprinting capabilities of Raman spectroscopy in polymers. As you can see here, I show you, well, 4 polymers, 1 fullerene, and one of the most promising non-fullerene acceptors. And as you can identify, all of them have a unique and vibrational fingerprint. For a complete list of materials, you can, well, I strongly recommend you to read this paper here because we have there this complete set of materials perfectly analyzed with Raman and also their cross-sections calculated. The point is that we've been working extensively during the last 2 years in trying to be quantitative with Raman. This means that our initial idea was quantifying the film thickness just by modeling the Raman intensity that we get out of a thin film, and also the volumetric composition in these films, especially trying to apply it to OPV blends. And the result was basically summarized in this paper. I skipped all the equations behind. We basically applied transfer matrix modeling to a typical Raman experiment, which we are taking into account all the interferences in the whole stack of your device or the supported film. And basically, this allowed us to extract the cross sections of the materials. We applied exactly the same approximation to OPV blends. This means that when we blend both materials in a film, we basically have to take into account the optical constants of the film, the Raman cross sections of the materials blended, and from here we are able to obtain the film thickness and the composition of the films. And this will be part of a talk that Mariano will give just after me, in which we basically exploit this technique to do mapping of thickness and composition in solar cells, and to extract easily the optimum parameters to obtain the optimum efficiency. And just to conclude, I would also like to highlight that we are now trying to exploit Raman also as a thermometer. This means trying to infer the thermal conductivity of thin films just by looking at how the Raman modes shift as a function of the temperature. And we can do this basically in freestanding films that we prepare by this process here, in which we basically deposit a water-soluble layer. Then we put our polymer of interest or material, we delaminate it in water, and then we laminate it again in basically a metallic washer, so that here in the middle the film is completely freestanding, and we can do our thermometry experiment. And this way we can get the thermal conductivity in plane of this freestanding material. And one of the most promising results we are getting now is that we are effectively looking at the anisotropy in the thermal transport by combining the Raman thermometry with the typical 3 omega method. We have been able to identify that in this polymer, the known N2200 polyera active ink, which is typically used in the fabrication of thin film transistors, that the thermal conductivity is fairly anisotropic depending on whether on the directions, if it is in plane or out of plane. Well, that's it. Basically, the take-home message is that you can use Raman scattering for several things: to study phase transitions, the degree of molecular order, quantify film thickness, composition in blends, and also to determine the in-plane thermal conductivity, which in combination with the 3 omega method allows you to look inside the thermal anisotropy in thin films. Well, just to conclude, I'd like to acknowledge all the co-authors of this work, as well as the funding agencies that made possible all this research. Thank you.
Thank you very much.